And now we're increasing the complexity of the problem at least twofold. What happens when the solvent gets involved, as in what happens when the solvent can be the nucleophile that adds, in addition to the potential nucleophile already present. And the other is what happens when the substrate that has the double bond gets more complex. And we're really going to address both of those thoughts with this video. And again, this is in the context of what happens when the pair of atoms that gets attacked in the first place, what happens when one of them has a lone pair on it and can stabilize the intermediate that might result. So of course the mechanism starts by the double bond goes ahead and attacks the more electrophilic end of the BR-BR bond, and that's because even though this is globally nonpolar, what if it becomes polarized and one end becomes slightly delta plus and one end becomes slightly delta minus? And again, the image to have here is that for whatever reason, this particular bromine is delta plus and this particular bromine is delta minus at the moment. And arbitrarily what I'm doing this time is having this kind of approach from the bottom side of the double bond. But the double bond goes ahead and shoots a pair of electrons towards that bromine, making a bond, which causes this to break. That will leave behind a cation at the tertiary position first, because that would be the more stable carbocation. But since this bromine has a pair of electrons on it, it can immediately add back in, and then that leads to the new product. And again, if I'm arbitrarily assuming that the bromine is coming from the bottom, then specifically the intermediate that would result is going to be the methyl is up, and that's because the bromine is now down on both sides, bound to both sides, and we would call that a bromonium. And you have this little triangle sort of thing that results from the set of arrows I'm about to draw. Now, of course, what I have here is a group that has a methyl on it. This one doesn't have a methyl on it, so arbitrarily I'm going to say, all right, the methyl's right here. And now let's go ahead and see what happens. Double bond comes down, kicks out bromine, pair of electrons comes back up, and again, that leads to this product as drawn. And now that I've done this, I'm going to go ahead and erase and reestablish what the actual product looks like. So, no other bromine involved anymore. The double bond that we had there is now largely gone and has been replaced by this bromine, which has more of an actual bond to the secondary side and more of a weaker bond to the tertiary side for reasons that I'm about to explain. But at least formally on paper, we would say that the bromine has a bond to each side, and formally we would describe the bromine as containing the plus. And again, I've drawn that by saying that, yeah, in fact, the bromine has the plus on it. But let's now consider what the double bond looked like in the first place. So what we had here was just simply a double bond, which ordinarily I would draw like that. But if we erase the pair of electrons and just draw the orbitals, then the pi bond was initially just a pair of electrons hanging out in two p orbitals as follows. And now that we've gone ahead and destroyed the pi bond, maybe those electrons aren't there anymore, and what we have now is just a huge bromine atom that's just sitting here and kind of interacting with both of those orbitals at the same time. So the bromine's basically like right there. And we indicate that by saying, hey, we've got a bond to both sides, and again, that's what I'm trying to show right here, but it's not going to sit necessarily directly underneath both atoms equally, but instead it can kind of rock back and forth as needed. And the way the bromine is going to prefer to sit is if it has a stronger bond to the one side and a weaker bond to the other. Said another way, the actual plus here is not going to be on the bromine itself. We have to draw it there formally because bromine doesn't like to have two bonds. But the plus is actually going to exist mostly on these carbons because we have polar bonds here. This bromine is electronegative relative to the carbons, so there's going to be more electron density on this bromine and less on the two carbons. What that means is that you actually have a fairly large delta plus at this position because that would be the tertiary carbon. The tertiary carbocation is more stable than the secondary. And this would be a smaller delta plus at the secondary position. And that's largely because this bromine is going to make sure that it sends more of its electron density in that direction and less of its electron density in that direction. And again, in practice, even though we're drawing the plus on the bromine, what that actually means is that you basically have these two orbitals right here that are both being donated into by this bromine. But the bromine is going to push more of its electron density into the secondary position and let the tertiary position more fend for itself. And that matters for what happens next. Now, of course, everything I've done over here is arbitrary. I assume that the bromine came from the bottom, but there's no reason to believe that. It could have come from the top as well. So in other words, I should also draw this potential product here at the same time. So you're going to make both. The bromine coming from the top, which is this product here on the left, and you're also going to make the one I drew originally, the bromine coming from the bottom. Alright, so at this stage, we would now have Br minus floating around nearby, and in the absence of any interaction by the methanol, at this stage what we could draw is the bromine coming in and doing some kind of addition products here. And for the sake of argument, what I'm going to do is show you what would happen. But keep in mind that the image you want to have is not sp3 hybridized carbons over there. The image you want to have is sp2 hybridized carbon with the bromine blocking one side. So if the bromine is sitting on top right here, then this bromine is going to have to come from the back because this is blocking access to the top side. But where is the bigger delta plus? The bigger delta plus is at the tertiary position. So in other words, this is going to be a product that is SN2-like in terms of stereochemistry, but it's going to be SN1-like in terms of regiochemistry. In other words, we have two questions to ask here. If this bromine were to attack, would it attack the secondary or the tertiary? The answer is, it would attack the tertiary because there's more plus there. That's the regiochemistry question. Which side do you attack? You attack the one with the bigger plus. So it's going to attack the tertiary, not the secondary. But it's going to be an SN2-like stereochemistry. It has to come from the back side because the bromine's sitting on top. So if I were to draw what would happen here with the bromine, well, what's going to happen is it's going to loop around and kick that out like so. And the product that you would draw here would be flipping the methyl up because the methyl was down. So now we're flipping that up and we're doing an SN2-like reaction. The bromine came from below because the other bromine was on top. And that would be one of the products that you would expect to form. Naturally, you could do the same thing on the other side as well. So that would lead to the other enantiomer. But this is merely a byproduct because the other thing that can happen here is that rather than the bromine getting involved, you could have the methanol getting involved. Well, this is the chemistry I'm more interested in because you wouldn't choose to run this reaction in methanol if you weren't interested in this product. And so here what's going to happen is the exact same sort of thing wherein you're going to attack at the tertiary position with the SN1 like regiochemistry because that's where the bigger delta plus is, but you have to come in from the opposite side of where the bromine is. And since the bromine is currently down, then that means the methanol needs to come in from the top. The methyl was up, so now the methyl is going to be down, which means that now we're going to have the methanol sitting right there with a plus on it because we have just done this addition and we have not yet done the acid-base chemistry, and the bromine will of course end up back because that's where it was to begin with, and it just now has an extra lone pair. So we attack this bromonium ion and now we have led to this cation where the oxygen contains a plus, but now of course we have more methanol floating around because methanol is the solvent, and methanol comes and does the deprotonation to finish off the final product here. And so what we actually end up making in this process is going to be the methyl ether, wherein now we have the methyl ether again is up, the methyl itself is down, and the bromine once again remains down. This is going to be the major product that we form in the reaction because again, if we were interested in making the dibromo species drawn here, then we wouldn't have used methanol as the solvent. We should use some non-participating solvent like dichloromethane. In both cases, of course, what you are making is the other enantiomer as well, or we would call this racemic. Again, if there's one particular take-home message from this video, it's to pay attention to the fact that the double bond is really made up of a pair of orbitals, and the bromine kind of comes and interacts with both of them and pushes electron density into both of them. And though we draw the bromine as having the plus, actually where the plus is going to be is on those two orbitals. And you need to think of them as being essentially flat. Drawn this way, it will give the impression of having sp3 type bonding at both of those carbons, and that's not really what's going on. It's more sp2-like, just with the bromine sitting there. And the bromine can kind of roll back and forth, so you're going to have a bigger delta plus on the tertiary position and a smaller delta plus on the secondary position, which means that the stereochemistry of the reaction and the regiochemistry of the reaction are governed by different processes. You're going to attack the place that has the bigger delta plus because one of those two will have a much larger delta plus. The tertiary will have more delta plus versus secondary. But you're going to have to attack from the opposite side of wherever the bromine is. And again, that's because the bromine is huge and it's basically blocking attack from wherever the bromine is. And so you're going to come in from the opposite side. So even though you can't run SN2 reactions on tertiary systems, you don't really have a tertiary here. You have something that's kind of flattened out quite a bit with the bromine sitting on one side. So you do an SN2-like stereochemical outcome, you do an SN1-like regiochemical outcome, and basically you have to attack anti to where the bromine originally came in. That will lead to a mixture of products as always, but if you were interested in avoiding the methanol getting involved, then simply choose a solvent that is not going to interact something more like, say, dichloromethane.